Sequential programming is a fundamental programming approach. In this example, the process consists of 4 steps. First, the circuit voltage is measured. Second, the user is prompted to turn on the power. Third, the circuit voltage is measured again. And finally, the user is instructed to turn off the power. Because LabVIEW is based on a data flow model, if the block diagram is arranged in this way, these 4 steps may be executed in an unpredictable order. LabVIEW provides a sequence structure that enforces a specific execution order within a block diagram. This structure is available in the Structures palette, and additional frames can be added as needed. In this example, the sequence contains 4 frames. The first measures the circuit voltage, the second prompts the user to turn on the power, the third measures the voltage again, and the final frame instructs the user to turn off the power. However, because this approach bypasses the data flow programming model of LabVIEW, the sequence structure is generally not recommended. A better approach is to rely on the data flow model to control the execution order. This can be achieved by wiring the error cluster between nodes to enforce sequencing. However, the one-button dialog VI used to display prompt messages does not include error cluster input or output terminals. To address this limitation, the dialog VIs are enclosed within a sequence structure, allowing input and output tunnels to be added. The same approach is applied to the second dialog box. As a result, the error cluster can be used to connect all 4 nodes in the block diagram and enforce the desired execution sequence. The preferred solution uses a case structure rather than a sequence structure. In this approach, the error cluster is wired to the case selector. If no error is present from the preceding VI, the structure displays the prompt to turn on the power and passes the error cluster through to the end, where the prompt to turn off the power is displayed. However, if an error occurs at any point, the error cluster reflects this condition, and the subsequent operations are skipped. As a result, the second voltage measurement is not performed, the user is not prompted to turn off the power, and the error is handled by the final VI, which displays the error message on the screen. The sequential programming pattern has several limitations. First, all steps must be executed in a predetermined order, and the execution sequence cannot be altered. Second, the program cannot terminate midway. It must complete every step before exiting. This behavior is unacceptable in applications where the program must stop immediately when an error occurs. For example, when controlling a machine, the program should be able to shut down the system instantly if a safety switch is activated during operation. A sequential program cannot respond in this way, as it must finish all scheduled steps before shutting down, which can be extremely dangerous. Consequently, the sequential programming pattern lacks flexibility and makes it difficult to extend or add new functionality.